Hey, we're back for the second part of the Chapter 2 lecture. We're still talking about Newton's first law, the first law of motion and inertia. This is part 2, and that's ugly. And remember that the class is conceptual physics, but really we're looking at a lot of misconceptions, things that we think we know that in fact our physicists say are a little bit different than what we experience or what we think we experience in everyday life. So it's okay if you have to chew on this for a while. We're going to jump into right into net force and vectors. So these other ideas we looked at in the first video, so we're going to move ahead partway through the chapter into net force and vectors. We're going to talk about net force, and the way that we describe net force is with a thing called vectors. Hey, if you are not familiar with the mathematical or the accounting way about net, another way to say that is resultant, or the overall, or when we take in combination all the different things, it's the net. If you have a checkbook or if you've got cash in your wallet, you put things in, you put things out, but at the end of the day, it's the result of all the actions that have happened. So when we talk about net, that's the combination of all the different things going on. When we talk about a vector quantity, and the important thing about a vector quantity is that it is a quantity. So vectors always have a number associated with it. We're going to represent vectors with arrows, so they always have a direction. We're not going to be so complicated in our class that we can't just go ahead and draw this on paper and have arrows that are pointing different directions. We're also going to try to draw our arrows bigger or smaller depending on the value of the vector. They're going to be drawn to scale. The length of it is the magnitude, and we're going to see this over and over again. Right now, we'll be talking about vectors with force. A couple chapters ahead of here, we'll be talking about vectors for velocity, for acceleration. So it's the magnitude, there'll be a number, and it'll be the direction, so there'll be an arrow on it. Yeah, the slide doesn't say it here, but it's also a pretty good idea to keep units with it. So are we talking about newtons? Are we talking about meters per second? Are we talking about miles per hour? Are we talking about meters per second squared? That way you make sure that your vectors are talking about the same thing. So when we look at a net, it's going to be vectors that are with the same units. So you can't put an acceleration vector together with a force vector. They're a little bit different animals. Don't panic. We're going to practice with this a lot. So the net force is the combination of everything that's going on. Let's give an example. Suppose that you've got a 5-pound or 5 Newton block, or a 50-pound sofa or piece of furniture, or a 500-pound sofa. It doesn't matter. And suppose that you are pushing on it on the same side, and you're pushing on it with 2 forces of 5 newtons. Well, that'll be a combination of 10 newtons acting on this block, on this thing. But if in fact you've got people on either side, each pulling with a 5 Newton force, the resultant is going to be 0 because they cancel each other. That's why the direction is really important, because it tells you whether or not the forces are cooperating with each other or canceling each other. Plain old algebra, just like a numerical timeline. Okay, here's your first quiz. Look at this. We've got a cart. So it's something with wheels on it. Think it's a skateboard maybe. It's getting pulled to the right from your point of view. Somebody is pulling it to the right with a force of 15 newtons, and somebody else is pulling it to the left with a force of 20 newtons. What's going to, from the cart's point of view, what does the cart see? What does the cart know? Does the cart see that it's got 5 newtons to the left? Does the cart see that it's got 5 newtons to the right? Does the cart see that it's got 25 newtons to the left, or does it have 25 newtons to the right? If you're able to, draw a picture. Pictures always, always help. Okay? Do you have it figured out? Well, this one is pretty dang easy. The result, the forces are in opposite directions, so they subtract from each other, and the direction that the cart is going to go is the direction of the larger force. So your cart is being, the result is that the cart has a 5 Newton force to the left. All right? Here's one with a picture. All right? You've got a block, it's got 10 newtons pulled to the right and 5 newtons pulled to the left. What is the net force? Is the result that we're 15 newtons to the left, 15 newtons to the right, 5 newtons to the left, or 5 newtons to the right? And in case you're like me, this is right, this is left. Who's going to win? Look at it for a minute. Notice that they've drawn the vector here bigger than the vector here. That helps. And what's the answer to this one? Well, of course, it's 5 newtons to the right. You could just do a little bit of math in your head, or you could say, hey, I'll take away this 5 newtons here, which leaves me 5 newtons left over. 5 newtons to the right is the net force. All right? Net force and vectors. So here's our vector. We've looked at the net force. Here's what a vector looks like. Always an arrow, different sizes, always is pointing some particular direction. It's a quantity. Magnitude, direction has an arrow. All right? Contrast this. And hey, I'll give you a hint. We're always going to work with vectors. We are going to rarely work with scalars. It's even okay if you don't remember what a scalar is. It's that thing that's not a vector. The difference between a scalar and a vector, they both have a number associated with it, a magnitude, a size. Scalars do not have direction. They do not have direction. That's important. Work with me. We're going to keep going. You'll get this. Leave those scalars behind for a minute. If we don't have a direction, we're not going to worry about it. We're only going to talk about things that have a direction. We're only going to talk about our vectors right now. And how do we get the resultant? In real world situations, this is exactly what structural engineers and architects work with all the time. In real world situations, you've got vectors pointing all sorts of different directions. How do you come up with the resultant, the answer, the conclusion? So when you've got multiple vectors going on, you want to come up with a resultant. And that's going to, in our case, it's going to be a sum. It's going to be sum addition. If the vectors are going the same direction, oh, that's a bad vector. And there's another one. If they're going the same direction, you just add them up, and they are a bigger vector in the same direction. Easy peasy. If they are going opposite directions, I'll give this a different color here. So if we've got one going this way and one going this way, but they're going the opposite direction, then you look at the difference. And that's exactly what we just had in the previous example. You subtract one from the other, the amount that's different is the resultant vector, and it's going in that direction. If they are at right angles, okay, remember what a right angle is? That makes a letter L. If they are at right angles, I'll make that fatter. If they are at right angles, whoa, look at that. Then you're going to have to go back into your geometry days pretend that they are legs of a triangle, and the resultant vector is the size and the direction of that. And I have just got to learn to be better at drawing on PowerPoint. Pythagorean theorem. We will practice this in class. Don't worry about it right now. You will remember it when we do it. If they are at other angles, we're going to follow what's called the parallelogram rule. Chances are on these, and an example of this would be maybe a vector that's pointing this direction and another vector that's pointing this direction. All right? What we're going to want to figure out is draw a parallelogram with that. And your resultant vector looks like that, except a straight line, of course. We will practice this in class. To actually get a resultant on this, to get a solution on this, you're going to have to use some trigonometry. It's not hard. We won't do it. It's outside of the math that's included for this. So if your vectors are not at right angles, we probably won't calculate a magnitude, a value of that, but we will look at generally what the magnitude of that would be and the direction of it, even if we don't put an exact number on it. Okay, here is an example of something that you would use the Pythagorean theory or kind of this logic of triangles behind. Imagine that you've got a bird's eye view. So you're looking through a hole in the ceiling. You're on the third floor. You're looking through a hole in the ceiling at the table or the floor on the second floor. There's a block. So you see down on this. There is something pulling it there's a force pulling it to one wall at a force of 30 newtons and another force pulling it to the perpendicular wall at 40 newtons. What is the, and somebody has already looked at this for you. So here is the resultant. The resultant is 50 newtons, and it's following this line of the triangle. What do we know about this diagram? What can we conclude from this diagram? So what's true here? Can we in fact say that the 50 Newton vector is the resultant of the 30 Newton vector and the 40 Newton vector? Can we say that? What do you think? Or, here's another one. Can we say that the 30 Newton vector is a component of the 50 Newton vector? Can we say that? Make all that go away. Or could we say that the 40 Newton vector is also a component of this 50 Newton resultant vector? Or, let me make that go away. Or, could we say that all of them are correct? What do you think? Think about it for a minute. Pause the video here if you need to. But how does this 30 and 40 and 50 relate to each other? Well, they're all correct. So what this is showing is that somebody has calculated this. What the experiment has had, what the experiment is set up for is a 30 Newton pole and a 40 Newton pole in these two directions. The resultant that we can calculate is this 50 Newton pole. These aren't three that are happening at the same time. The yellow ones happened first, and the resultant is showing the combination of both the magnitude and the direction of the first two. We will practice this in class. If you don't get it yet, don't panic. Here's a little bit more real world example, and the guy who wrote your textbook really started out as a cartoonist before he was a physics teacher, so you got a lot of fun drawings. He calls this chick Nellie Newton, and she is hanging from a couple ropes. So her rope is attached here and here to the ceiling, and her ring is in the middle. She is hanging from it. And she is on Earth. She's got gravity acting on her. So this one is gravity. It's pulling her down. Which rope has the greater tension? Which rope is working harder? These ropes do not stretch. If they were stretchy, what would happen? And we've also got little gauges on here, and we will play with these in class, which will tell you the tension, the pull on these ropes. Which one do you think is acting? Which one do you think is pulling harder? Well, there are three things happening to Nellie. Nellie is not moving right now. She's got the weight pulling her down. She has got the tension in this rope pulling her up, and she's got the tension in this rope pulling her up. She's not moving. What's happening here? Well, because there are different angles, there are different rope tensions. Nellie's at equilibrium. She's not moving. Her weight is totally supported by these two ropes. So this resultant right here is equal and opposite to the gravity that's pulling her down. These ropes are pulling her up with the same amount of force that the ropes are pulling her down. We've got a parallelogram rule. Yeah, it might be Pythagoras. So we calculate from this what the right angles are, so that we can come back and say, gosh, this resultant is from a force this way and a force this way. And look, we don't need numbers. We can see that the force on the shorter rope is greater than the force on the longer rope, and that has to do with the angle. All right? So that's your eyeball evaluation of how the resultant force comes from the component forces. All right, let's move ahead to the equilibrium rule. Old Nellie on that rope was at equilibrium. She was neither moving up nor down. She was a body at rest, staying at rest. She had equilibrium. All right, we will do this in class. If you take a weight and measure the newtons on it as the force of gravity, the string is holding up the bag of flour. There are two things happening with the bag of flour. It's got the force of gravity pulling it down, and the string pulling it up. All right? They are equal and opposite. It's at equilibrium. That bag of flour is not moving. Hey, funny thing, the guy in this picture, your author in your textbook talks about the other sign painter on the scaffolding, on his tension examples. This guy is Burl. Apparently, he hired a private investigator to go find his sign painting colleague years after he was done sign painting. And this is the guy, this is the other little man on the diagram. So this is Paul, who's the author of your textbook, and this is Burl, who was the dude in the last photograph. Isn't that funny? So his example that he uses in the book is standing on the scaffolding with ropes hanging down. Both of the painters have a force of gravity acting on them. They are downward. And thankfully, they've got good ropes holding them up. And that is the force upward. We'll do a lab on this in class, but the forces, the net force is 0. The scaffolding doesn't move. We don't want our painters flying around. So the question that you've got with this, what are the forces on the two, what are the forces that these two ropes hold to maintain equilibrium? When we add up the vectors, the total is 0. It's a system in equilibrium in that this is not moving. Okay? And here's the same thing that I've just been saying. The red arrows are the force vectors. The magnitude of the 2 upward are exactly equal to the magnitude of the 3 downward. The 3 downward is the gravity from the 2 painters and the mass of the scaffolding itself. Here's another quiz for you. The equilibrium rule. We did not say this, which is bad. If you're not familiar with it, or even if you are familiar with it, that is the Greek letter sigma. That's the capital Greek letter sigma, which stands for summation or total. You're going to see that a lot. You'll see it in accounting terms. You'll definitely see it in math and science. So what this is saying, the equilibrium rule, is that the sum of all the forces equals 0. Here's your quiz. Does this apply to vector quantities? Does it apply to scalar quantities? Does it apply to both vector and scalar? Or does it apply to neither vector nor scalar? Think about that one for a minute. When we talk about the equilibrium rule, are we talking vector quantities or scalar quantities? What do you think? Well, vectors, 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 vectors. Your scalars, it doesn't work. Scalars don't have direction. So we can't be looking at one canceling or adding to another. So our equilibrium rule is going to always be vectors. Remember what a vector is, though. It can be different things. So your vector can be force, can be speed, can be acceleration, and it works when all the vectors are the same. So you can't add a force vector and acceleration vector. They don't work. And you can't add a scalar to a vector. And the nice thing about it being a vector is that it makes our magnitudes positive and negative. So you can, in fact, when something is not moving, you need to see what the forces are that keep it at 0. All right, we've talked about our net forces briefly. We're going to work on this. We've talked about the equilibrium rule, which is saying when there is no net force, when everything adds up to 0, your brain should be saying right into, well, gosh, everything's got gravity acting on it, and why isn't everything always flying around? And here we're going to go into the support force, also called the normal force. You'll probably catch me calling this normal more often than... Okay, I got to figure out a better way to write on these. Normal, that's ugly. And I'm going to erase it. Our normal force is telling us why a book on a table doesn't fall to the floor. It's probably more correct to call it a support force. You'll hear both of them. And the normal force is what we call the table on the book. The thing that's keeping something that's going opposite of gravity. Normal forces are always opposite of gravity. And the word normal is coming not from the fact that it's normal as opposed to being odd, but it's normal in that it's perpendicular. It's a right angle. Uh, uh, the book on the table is pushing against the table, and the table is contacting the book. Another example, another experiment that we'll do later on is play with springs. If I push on a spring pushes back. We'll actually have a lot of fun playing with those. When the book is pushing at the table is pushing back on the book. That is absolutely intuitive. You know that books don't go falling through tables. Ah, here we've got another drawing. Here we've got another example. You've got two bathroom scales. You've got your foot on each one of them, and you are perfectly in between the two. What do the two scales measure? Does each scale measure your weight? Does each scale measure half your weight? Does each scale measure 0? Or does each scale measure something more than your weight? What do you think is going to happen? If I can find the scales, this is an experiment that we will do in class. All right, let's see if we can draw a picture with this. It's always better to be drawing a picture. So we'll make gravity green. You are standing on a scale. And you're pushing downward with the amount of force equal to your weight due to gravity. All right? You are at equilibrium. You're standing still. You're not flying around or anything like that. So these scales are pushing back. When we add these two vectors together, they have to equal the magnitude of this one. And you are even, we said in the example that you are evenly balanced between the two scales, so these each share half of your weight. You are at equilibrium. You're at rest. Your force down has to be canceled by your force up, so each one is 1/2 your weight. Something to think about: what happens if you shift to the left or the right? What are those scales going to look like? And that's an example we'll play with in class. All right? We've talked about equilibrium. We've talked about things being still. We've talked about what the forces are that keep you still, opposing gravity. Let's talk just a moment about things that move. We will spend chapters and chapters and chapters looking at how things move. So we're just going to introduce it here right now. This is tough. You thought inertia was bad? This is going to be tough. We can have inertia on things that are moving. Static equilibrium is when something doesn't move. That's when the bowling ball is just sitting still on the floor. Nothing has happened. Dynamic equilibrium is the movement that's going on after the force has stopped. It is the soccer ball flying after you've kicked it. It is the bowling ball rolling after it's gone down the inclined plane. It is at equilibrium. It's not going to change unless there's a force on it, but it can be moving. All right, here's another example. If something is changing its motion, if this crate is not moving, it's at static equilibrium. When we are pushing it at a steady speed and no change in direction, it is a dynamic equilibrium. Here's the first time that we have seen friction come into play. When we are looking at equilibrium, friction is one of our vectors that we will look at. It's going to be like the normal force, and it's going to be opposing a motion. A common sense way to look at this, if this were on a driveway and the worker was pushing it, compare that to if it were on ice or rollers and he were pushing it. All right? Friction is the difference between this thing sliding and not sliding. Another question, another quiz for you. We've got, and you should do really well on this one. A bowling ball is at equilibrium when it is A, at rest, B, moving steadily in a straight line path, like down our hallway perhaps. Both of the above, are these both conditions of equilibrium, or neither? You don't get any time to think about this question. You know the answer to this one. It is at equilibrium either when it is sitting still or moving in a straight line with no change in speed or direction. Equilibrium does not mean an absence of motion. It means that there is no change in motion. If it's at rest, it stays at rest. If it's at motion, it stays in motion. What is this? This was in the last lecture. This is Newton's first law. An object at rest stays at rest. An object in motion stays in motion. All right, here's a quiz. Nellie has come down off of her ring. She's now taking over pushing the crate. She is pushing a crate in a steady state. It's just been given to you that the magnitude of friction you need to overcome is equivalent to 75 newtons. How much does she need to push? More than 75? Less than 75 newtons? Equal to 75? Or you don't know? Think about it. If the friction force is opposing her at 75 newtons, what level of force does she need to push in order to achieve a steady amount of motion? She's got to push exactly 75 newtons to overcome friction. Is she going to go fast? No. Is she going to accelerate? No. Is she going to achieve motion to get out of equilibrium? Absolutely. We've talked about a variety of these Renaissance scientists. Here's Copernicus, and he's roughly the same time as Galileo, a little bit ahead of Newton, and he's one of these thinkers. He's one of these theoreticists, and he comes up with the controversial idea that the Earth circles around the sun. This got him into a lot of trouble because the rich people, the powerful people, thought that everything revolved around them, that they were the center of the universe. It's kind of hard to admit that you're not. Here's the question. Here is the question. If and something that Copernicus had to deal with. If the Earth is moving, that means that the tree is moving. If the Earth is rotating. So the bird trying to catch the worm, how can he or she be moving while the Earth is moving? How can that work? We're coming into something intuitive. This is something that y'all have dealt with since you could throw a ball. this is where our friend inertia comes back, because it looks, to your eyeballs, it looks like the bird is not moving, but in fact, the bird and the tree are moving at the same rate. So there is inertia happening, and while the bird, to you and me, while the bird looks like he's flying down, in fact, his motion encompasses both this downward motion and the motion of the Earth, rotational motion of the Earth. It's okay if you don't understand it right now. We will work with this a lot. All right, here's your quiz. You are on an airplane. You are bored. You've seen the movie before. You're ready to be done. And you are flipping a coin because you're doing a physics experiment on your airplane. Where's this coin going to land? Is it going to land behind you? I'm presuming you're in a forward-facing seat, so you are going this way. Your plane is going that way at several hundred miles an hour. Where's that coin going to go? Is it going to go behind you? Is it going to land ahead of you? Is it going to land in your hand? Or do you not know? Where's the coin going to land? It's going to land in your hand. And the reason